All right, so welcome to day 2 of environmental toxicology. So before we can really dig into some topics, we've got to get familiar with some of the main compound classes and general ideas that we're going to be seeing. So this lecture and the next will be mainly focused on just sort of introducing some compounds, things about them, why they are included in environmental toxicology, and just some general information about them. So your textbook has several groups of chemicals that they would like you to consider. This is by no means an exhaustive list of chemicals that can be considered in a toxicological sense, but these are kind of the main players. These are the primary ones that we tend to encounter in an environmental toxicological setting. Within each one of these categories, there are lots and lots of compounds. Some contain several permutations, some contain several thousand versions, especially as we get into these later organic compounds. Really anything we can engineer could be included in that category. So there's really no way to know every single chemical that you could possibly encounter in these kinds of scenarios. But this will introduce you to these general categories and some typical traits you might expect these compounds to exhibit. All right, so before we really launch into these, one of the main features that we're going to be considering about these compounds and these compound classes is their solubility. When we talk about solubility, we're mainly thinking about their ability to move through an organism. Now when we think about humans, and we think about what humans are made of, what do you think is the largest component that humans are made of? What's the stuff that makes up humans the most? Water. So we are mostly made of water, but we're not only made of water. So we're, yes, mostly made of water, but we're also made up of a lot of cells. And what kind of, if you think back to Bio 109 of our sort of 4 main macromolecule classes, what is the primary macromolecule that makes up cell membranes? A lipid. So we're a lot of water, but we're also a lot of cells that all contain a lot of lipids. So we have to think about how chemicals are going to interact with water, but how chemicals are also going to interact with those lipids, like our cell membranes. And so we want to think about that solubility. So we tend to think about chemical compounds either being lipophilic or lipophobic. So excuse me. So both of these terms here have lipo as a prefix. And since we already said that cell membranes are comprised mainly of lipids, I think everyone can clue into what the lipo part of these words is referencing. Hopefully that you've got lipids or fats or whatever you want to call that macromolecule group. And so then we've got the philic or phobic part of this. So who remembers what philic means? What does philic mean? Attraction to, yeah, it likes interacting with that kind of thing. So substances that are lipophilic tend to like interacting with lipids. Yeah, so they tend to like interacting with lipids. These are compounds. There we go. Come on. There it is. All right, so these are compounds that tend to be non-polar, right? Lipids are famously non-polar. Butter does not like to go into water, things like that. So these are non-polar compounds, meaning that they're primarily lots of carbons, lots of hydrocarbons. Things like lipids, right? Lipid like attracts like in this kind of instance. So lipophilic compounds tend to look like lipids. They have a lot of carbons, lots of hydrogens. They tend to be pretty non-polar overall, and they tend to be fairly large chemical structures. So I've got here a couple of examples of some lipophilic compounds like cholesterol, right? We've got, I'll use the pointer on here so that you guys can see this on the recording. So we've got cholesterol here as an example of a lipophilic compound. So you can see there's lots of carbons. We're going to see a lot of chemical structures like this. And so if you're not familiar generally with what this chemical structure is showing, just out of curiosity, very quick, has anyone here taken organic chemistry? All right, handful of people. Okay, so For those of you who haven't taken organic chemistry, when we draw things like this, so when we draw something like this, what we mean with this is we mean that we've got carbon connected to carbon connected to carbon. And you can see how long this is taking me to write and draw. Is why in organic chemistry, no one actually does this. They just draw that. So anytime you see any sort of chemical compound that just has a whole bunch of lines, anytime you have two lines needing to form some sort of an angle, imagine there's a carbon molecule or a carbon atom there. Does that make sense? Okay. Okay, so a little sidetrack there. Okay, so we've got our large lipophilic cholesterol here. Another famous lipophilic molecule is THC, and you can see that THC has a lot of the same properties as cholesterol. Lots of hydrocarbons, pretty big, some clumsy rings in here, and generally speaking, non-polar. Especially when we talk about things like polarity or solubility, there are very few absolutes. Molecules tend to behave primarily lipophilic. They tend to be primarily non-polar, but that doesn't mean they are absolutely non-polar. It doesn't mean they are absolutely lipophilic. They all just sort of tend to prefer. If you put oil in water and give it enough time, it will eventually go into that solution. It may take a couple hundred years or 1,000 years, but it'll happen. So this is really just sort of a trend. And so I've got everything here on a gradient because there is no absolute. All of this is on a gradient. So these are some examples of compounds that tend to be lipophilic. Like, for example, on this cholesterol, we've got this hydroxide group hanging out here. Anytime you see a hydroxide functional group, what did our functional group table from last time tell us was the property of hydroxide? Polar. We've got a polar group on a non-polar molecule. So this little bit right here, this is going to be particularly reactive if it's going to react at all. And so this is why none of these compounds are any sort of absolute. They just tend to be more lipophilic or not. Does that make sense? Okay. All right, so there's our lipophilic compounds. When we think about lipophobic compounds, so if philic means loving, what do we think phobic means? Fearing, don't like to interact with. So these don't like to interact with lipids. They would prefer to interact with all that water that you've got in you. So these lipophobic compounds tend to be very polar. And if we look at our examples, we've got oxygens, we've got hydroxides, we've got more oxygens, we've got nitrogens, we've got all sorts of things that are going to have electrons hanging off of them, ready to interact with water. All right, so we've got our lipophobic compounds. These tend to be polar, they tend to be smaller. I realized that my sizing could have been better. I could have made the ring size here for aspirin match the ring size here for cholesterol. But you can see that there's only one little itsy bitsy ring here in some pieces, rather than 4 rings and some giant satellite antennas hanging off for cholesterol. So aspirin tends to be an example of a lipophobic compound. First to interact with water. Caffeine is another example. This is why caffeine, why we tend to drink pretty watery things when we're trying to get caffeine, tea, coffee, right? We're putting these things into hot water to liberate the caffeine from the plant matter of the tea or the coffee so that you can then drink it and incorporate it. And if you've ever had too much tea or coffee, you can tell because you smell it in your urine, which is primarily water, right? When you go to the bathroom after you've had 4 espressos, it smells like you've had a lot of caffeine because it's going into all that water. But again, these are not absolutely only lipophobic. They won't only interact with water because this is a pretty big hydrocarbon thing here. It can have some non-polar properties. It can have some lipophilic properties to it. Again, we have some ring structures here that gives it a little bit of oomph. One of the things that we do to our coffee quite often is we put cream in it. That cream helps get even more caffeine out because it gives it another place for all of these other carbons to interact with so that you get absolutely the most caffeine out of your coffee or tea as you possibly can. All right. So In addition to lipophilic versus lipophobic, sometimes we can call these by their inverse synonym, which I realize doesn't make too much sense. But if you think about things loving lipids, what does that say about their likingness or not likingness of water? You think things that like lipids like water? No. So things that are lipophilic are also hydrophobic. Things that are lipophilic are also hydrophilic. So we can talk about these things being hydrophilic. We can talk about these things being hydrophobic. So they are their inverse synonyms, right? So lipophilic is the same as hydrophobic. Lipophobic is the same as hydrophilic. Just in case you see that in the literature, if you're reading a primary article and they decide to use the hydro term rather than the lipo term, be aware. Your textbook uses the lipo terms, and so that's what I've defined here. All right. So let's start off with some inorganic metals, which is a little bit redundant. Of course, metals are inorganic. They don't contain any carbon. They are metals. Metals are typically good conductors of electricity, and they will often enter into chemical reactions as a cation. Does anyone remember what it means to be a cation? They have a positive charge. So these are compounds that very often have a positive charge to them. I always remember that cations are positive because I like cats. So anytime I have a cat, that's a good thing. All right, so we have metals entering reactions mainly as cations, meaning that they're going to be looking for functional groups that tend to have a negative charge. So things like oxygens, things like phosphorus, all sorts of negative charges is what they're going to be looking for. They've been around for a long time. We've got lots of metals all over the earth, and metals, because they are so ubiquitous on Earth, because they're everywhere, all the metals that we have are natural. They exist. It's really hard for us to sort of make a new atomic metal. Lots of metals are essential, right? We'd be pretty lost without iron. We need some metals, but quite a few of them are hazardous. We don't need too much mercury in our diet. So metals comprise lots of different roles. We often encounter metals in an environmental toxicological condition or situation through mining activities. Because most of our metals are found within the Earth's crust, it's sort of really hard for them to just get exposed. So we typically expose them to humans through mining activities, digging into the earth, bringing things out into reacting with the air, right? Air has oxygen in it. Oxygen is negatively charged. Our metals are positively charged. They form a reaction. So we bring our metals out from the earth into the air. They react. There are some natural ways that metals can get interacted with organisms on the surface through landslides, floods, hurricanes, wildfires, etc. So there are other ways, but in a tox sense, mostly it's through mining activities. One of the things that metals do most often is they form covalent bonds with compounds, and they transfer electrons. Most notably, they'll react with either free oxygen or these hydroxide groups. They can sort of remove them in the electron transfer process and just have free hydroxides ranging through the organism's body, or and then they'll form a covalent bond with whatever that hydroxide group was taken off of. If we want to know about how much more of a particular metal is in the environment than maybe there should be, one of the ways that we can measure this is through a metric known as the anthropogenic enrichment factor. So the anthropogenic enrichment factor is a metric that describes the level of human contribution of a particular metal to the environment. Is this thing in the way? Okay. All right, so this is a table from your book. I think I've abbreviated it. I don't think I've included anything, but it's got, or included everything. But these are some metals that we could consider. So here we have some metals. And here we have some unitless amount of that particular metal that is derived from anthropogenic sources. So remember, anytime we see anthropogenic, this is our human created source. We're going to compare that to its natural sources, and then we will calculate our anthropogenic enrichment factor. So just to map this out, the way this goes, you would take your anthropogenic, add it to what's present naturally, i.e. background. That gives you your total, and then you would divide 8, the anthropogenic, by the total, would give you 89%. So what this first line is saying is that 89% of the cadmium in the environment is coming from anthropogenic sources. So the anthropogenic enrichment factor of cadmium in the environment is 89%. For lead, the anthropogenic enrichment is 97, so on and so forth. So we can calculate that for almost any of our metals. And it's a good thing we've got a tool to measure this, because the vast majority of elements on the periodic table are metals or metalloids. They're not, they're not fully metals, but we've got lots of metals on here, and these metals span really the whole periodic table. We've got lots of really important metals that we need over here: sodium, magnesium, potassium, calcium, some important metals over there. Here's tin, here's lead. Where's our silver and gold? I always forget which one is which. Mercury, very similar to those. Chromium we need, manganese we need, iron we need, cobalt we need, copper we need, nickel we need, zinc we need, right? So a lot of these we tend to need. We tend to find more of our metals that are useful to us organisms in this sort of top row of the transition metals here in the middle, and these sort of lighter metals in these first two families of the periodic table. So these metals tend to be useful. These metals tend to be useful across the top here. And then you start to get slightly more toxic as you increase in atomic weight. These guys down here are incredibly toxic. So there are some trends that we can notice, but there is no escaping metals because they do comprise most of the chemicals that we have on the planet. Those covalent bonds that chemicals can form have lots of toxicological consequences. One of the things that these covalent bonds can do is often to make compounds more lipophilic than they previously were. One of the consequences of that increase in lipophilicness is that it makes it a lot easier for your body to store those compounds, right? Like if like I've got some excess fat deposits, and so if I were to be contaminated with metals and they were to react with some organic compounds, they would get stored in my lipid deposits. And then as, let's say I then went out and wandered in the desert for 40 days and 40 nights, and my body would then start to utilize those lipid stores. And so then, even though I'm not eating anything, even though I'm not exposed to anything, I am still then latently being exposed to those metals because it is being released from my lipid stores. So when metals interact with organic compounds that were not previously lipophilic and makes them lipophilic, they now become something that can be stored. This is one of the reasons why lead tends to become so dangerous for children, because children have baby fat on them. They've got a lot of baby fat, and then they hit that growth spurt and they mobilize all that baby fat, and then they sort of get this like consistent, persistent dose of metals that can harm them over a persistent period of time, even though the initial harm may be long gone. Some other things that these covalent bonds can do is they can malform proteins and other enzymes that our bodies find useful. So one of the particular ways in which this can happen is metals can react. Certain metals like copper, mercury, lead, and arsenic They are particularly reactive with sulfhydryl groups. So the amino acid cysteine has a sulfhydryl group. So if you have a protein that has a lot of cysteine in it, this protein is going to be particularly susceptible to these metals. If you have other enzymes and other compounds that have some sulfhydryl group, a part of them outside of cysteine, these are also susceptible to lots of different metals. These metals will either bind to the sulfhydryl group and make a big kink in the protein, or they will remove that sulfhydryl group and remove some hydrogen bonding that was keeping that protein in a conformational shape. One of those key things, one of those key examples of metals interacting with proteins and enzymes, malforming them, making them not work, comes to us from pyruvate dehydrogenase. And, you know, I can just say pyruvate dehydrogenase and everyone says, whoop-de-doo. Who cares about pyruvate dehydrogenase? Well, pyruvate dehydrogenase is one of our entry enzymes into the Krebs cycle. So if you don't have pyruvate dehydrogenase, you have a really hard time making enough acetyl-CoA to do the Krebs cycle. So you're missing out on all of the oxidation that happens with, and all of the electron carrier creation that happens in the oxidation of acetyl-CoA. You miss out on all that. You miss out on all of the things that happen in the citric acid cycle if you happen to skip that step. It's not impossible for you to generate some electron carriers and make ATP if you're skipping pyruvate dehydrogenase, right? We learned in Bio 109 about other entryways into the Krebs cycle that bypass the acetyl-CoA pyruvate dehydrogenase step. But when we consider that most of our energy comes from glucose that necessarily travels through pyruvate, that's a pretty big cut in available ATP that we are losing out on just because some metals interacted with the sulfhydryl group. And there's the sulfhydryl group that we are particularly interacting with. We're missing out on a lot of energy creation. All right. Everybody good so far? Holler if I'm going too fast. Okay. So within metals, some metals are good, some metals are bad. We used to classify the bad metals as heavy metals. And a heavy metal previously was classified as some metal that had a density ratio, and let me say ratio here, relative to water, of above 5 or above. So if you recall, the density of water is 1, right? 1 gram of water weighs, or 1 gram of water takes up 1 milliliter of volume. So the density of water is 1 gram per milliliter. And so we could calculate the density of some metal and then make a ratio of whatever that number is over 1. And that would be our density ratio. So we used to call heavy metals anything that had a density ratio of 5 or greater. So this was when we were really looking at those lower on the periodic table metals. Now we're much more concerned with metals and their ability to chemically react in a negative way. And so the term heavy metals, it still gets used, but it's considered less important from a toxicological perspective than the actual chemical reactivity. So for example, aluminum. Aluminum has a density of 2.7, so less than that 5 ratio, but it is considered a fairly toxic metal. It has a lot of chemical reactivity. We use aluminum for a lot of different things, but it has a lot of negative consequences. We often find in acidified lakes, we will see fish gills that are broken down a little bit by excess aluminum that tends to precipitate, or that tends to dissolve more easily into acidic water. So when water is acidic, it can take in more aluminum. And as fish try to breathe and extract oxygen, the aluminum gets stuck on all their gills and can cause these lesions. And so here are some micrographs of fish gill. So here's a normal healthy fish gill. You can see that there's nice clean margins to the lamellae on that fish gill. And then on this one is damaged by aluminum. This one is damaged by aluminum. And you can see how the margins are much less clean. There's all these kind of little pockets or holes in those lamellae. And that's negatively affecting this fish's ability to uptake oxygen through those gills. This is absolutely not my field of expertise, and I have not dug into the literature extensively, but there is a decent body of literature out there showing that implicating aluminum deposits in human brains associated with Alzheimer's and other dementia-like diseases. So I am not saying that aluminum causes dementia. I'm not saying that. I am saying that there is a strong association between dementia-like symptoms and having aluminum in your brain. That relationship exists, but to say that one causes the other, I don't know if the research is there yet. All right, so aluminum, yeah, so that's aluminum. So instead of using this whole heavy metal thing that doesn't really necessarily work anymore, we've instead switched to that chemical reactivity. And this is another table from your book that has broken down those metals into what kind of chemical reactivity we might anticipate from those metals. So we have some metals here that are oxygen seeking. So these are metals that are going to react with freely available oxygen or even a hydroxide group. So calcium, magnesium, manganese, etc. These all tend to react more with oxygen-based compounds. Here are some metals that tend to react more with nitrogen or sulfur compounds. And then these are metals that can go either way. They don't necessarily show a particular preference for either oxygen or nitrogen or sulfur. So if you were looking at a habitat and you noticed that, say, that there was a lot of, let's say you noticed that there was a lot of potassium in that habitat, would you expect potassium to be of concern for organisms' proteins? So let's think about what a protein is made out of. What is a protein made out of? What are the monomers? An amino acid. An amino acid is the monomer of a protein. What is the chemical backbone of an amino acid? So the backbone of all amino acids, right? All amino acids have the same basic chemical structure, right? We've got that terminal amino group, got carbon in the middle, another one. We've got our carboxyl end here. Oh, got my oxygen. There we go. There's put our R group up there, our functional group. H, and then I'm gonna get lazy here and just write H. Great. Okay. So here's our basic amino acid. Now, when you have a protein, you have just one amino acid. Now, you link them all together. You have a bunch of amino acids. And where do amino acids attach onto one another? Not at the R group. Because the R group is what makes that particular amino acid that particular amino acid. If you remove it, you've got nothing. So we can attach things to the C end. So if I change my ink color here, so let's go with blue. All right, so now I can lop all this off. And we've got another amino acid over here. And if we wanted to attach one in the other direction, we would lop all this off and have another one over here. All right, so we've built a little basic protein with my shitty little diagram. Okay, so we're looking at potassium. And we're wondering, is potassium a concern for organisms' proteins, enzymes, things that make the organism work? So potassium is oxygen seeking. In our 3 amino acid length protein, do we have more oxygen or do we have more nitrogen? We have more nitrogen than we have oxygen. So Are we worried about potassium attacking this protein? Not necessarily, not as much. What kinds of metals would we be concerned about attacking this protein? The nitrogen-seeking ones are class B, so cadmiums, coppers, mercuries, silvers. Right, because even though, yes, this carbon over here will have some oxygens on it, because that's the end of our little protein here, but it's just those oxygens. In this little protein, we've got just some one or two little oxygens hanging out there, but we've got 1, 2, 3 nitrogens all throughout that it could possibly be interacting. So instead of just classifying things as it's dense, it's a heavy metal, therefore bad, rather we're concerned about its chemical activity. And so when we say chemical activity, this is an example of the kind of chemical activity that we need. All right, and then additional reasons to be concerned about metals is once you have metal contamination in your environment, it's really hard to get rid of it because metals as elements don't break down. Right? Iron is always iron, is always iron, is always iron. It doesn't break down. So once you have a contamination of chromium, you're stuck with that chromium unless you physically remove it. I recently attended an EPA planning session in the town where I live in Niagara County, where they're going to do some remediation on 18 Mile Creek as it comes out from underneath the Erie Canal. And they're doing some remediation because there's all sorts of PCBs and lead in the river sediment of 18 Mile Creek. And what the EPA's plan to do is they're going to, this is their plan. They're going to dredge the river. They're going to come in with some heavy earth moving equipment and they're going to dig up, I want to say, they're going to dig like a foot, either a foot or 2 feet, I can't remember now, a foot or 2 feet down into the riverbed, scoop all that sediment up, put it on a truck, and take it to a hazardous waste disposal site. And they're going to do that for several hundred feet length of river. And they have to do that to the riverbank, and they also have to do that to the land on either side of the river, because that also has the lead and PCBs that then just wash right back into the river. So to remove all of that soil, this is their best plan to remove this. And this is true not only for this one 18-mile site, but generally nationally, this is our best way at dealing with metal contamination like this, is you have to remove this. That's going to cost $60 million to remove that dirt. And the vast majority of that cost, because they showed us the cost, they showed us like 4 plans, like here's 4 things we could do, here's the cost for all of these, to just kind of try and filter the water, but not actually do anything with the sediment, was a couple $100,000. It wasn't cheap, but it was a couple $100,000. And then as soon as you start talking about digging things up, so first they were going to dig things up and just put it somewhere, and that was a couple million. And then as soon as we started putting the metals in a hazardous waste facility, that's when we started to get into the 40 million, 60 million, $80 million to deal with this sediment. So it's really the storage of these contaminated soils and sediments that really gets to be expensive. So, dealing with these metals, you can't just kind of wait for them to go away. That's it. They're there. The only way to get rid of them is to just remove them. All right, but not all metals are bad. Some are good. We need lots of them. If you take your daily Flintstones chewable, you're probably getting a smidge of all of these. I think vanadium might be one of the ones we need the least. I don't know what we need vanadium for metabolically. If somebody wants to do an honors project on what we need, what we need vanadium for, I'd be up for that. Some plants need boron. We don't really need a whole lot of boron. But any metal can be toxic if you eat enough of it, or if you consume enough of it, or are exposed to enough of it. We do need a pinch of chromium, but we don't need very much chromium. So for essential elements, if you're below some level, we call you in deficiency. And then if you're in some particular window where you've got enough, your metabolism is firing optimally. And then once you cross that upper threshold, that's where you start to have too much of that metal and your metabolism starts to tank. And now we call you that your situation is toxic. You have too much. For some particular metals, there can be no effect for very low concentrations. And then all of a sudden you cross some threshold and then you're toxic. So these are primarily for non-essentials. So if you have just a little bit of lead, like parts per trillion amounts of lead, not that you should go out and eat parts per trillion amounts of lead, but if you were exposed to parts per trillion amounts of lead, that's probably fine. But as soon as you start to cross into that parts per million, downhill. Interestingly, some metals can induce deficiency of other metals. So think of this like, think of these like coins. You know, let's say you needed to spend, let's say in order to do an efficient metabolism thing, you had to spend 7 cents, right? There's lots of ways to come up with 7 cents. But if that 7 cents has to be in the form of 1 nickel and 2 pennies, that's the only way you can spend that 7 cents. If you don't have any nickels, use the pointer so that it gets recorded. If you don't have any nickels, then you can't spend any copper. There's supposed to be the word deficiency, copper deficiency in cattle. I don't know what happened to the rest of this. Hang on just 1 second. I want to try and fix that. There we go. That's how it is. There we are. That's better. I knew I had the word deficiency in there. Copper deficiency in cattle. So if you don't have any nickels to spend, then you can't spend those 2 pennies, even if you had them. Even if you had 30 pennies, you can't spend any of them if you don't have any nickels. If it costs you 1 molybdenum in order to use a copper, you've got plenty of copper, but no molybdenum, then you can't use that copper and you are functionally deficient in copper. Does that make sense? Okay. Okay. So very quick vignette into one of the great metal toxicological stories in recent history. And we're going to go look at Flint, Michigan. Folks heard about Flint, Michigan. All right. So Flint, Michigan, this is now bordering on happening almost a decade ago at this point. But so here's the town of Flint, Michigan. So here's Detroit kind of down here, and then you start to go up into the thumb of Michigan, and there you are at Flint. And for a long time, Flint was sharing its public water supply with that of Detroit. And so here's Detroit. Detroit's down here, and they were mainly getting their water from Lake Huron. So we're sort of up here in the state of Michigan for those who know how to do the hand geography. So Detroit's down here, Flint's up here. Everybody's getting their water from over here. For those who know the hand geography of Michigan. So there are all these pipelines coming from Lake Huron. Lake Huron's pretty clean as far as Great Lakes water goes. This Lake St. Clair right here is not so great for water quality. There's a lot of shipping and industry contamination issues, and so they don't tend to get their drinking water from Lake St. Clair. Instead, they come up here to Lake Huron. They've got this series of pipes that pipes in and then down into Detroit. And for a long time, Flint was sharing that. And it was getting to a point where Detroit was trying to charge Flint a little bit more money for sharing their water supply. And the infrastructure was getting really old and ready for an update anyway. And so there was a proposal for Flint to build new pipes to get their own water from Lake Huron so that they did not have to rely on the city of Detroit. All well and good. But then the city managers of Flint saw the price tag for the building of that new pipeline and said, that's way too expensive. We've got this whole river right here. Why not just get water from the river? And so that's what they did. And so this river and a lot of this land up in here, a lot of this land looks a lot like Niagara County. It's very agricultural, pretty rural, some industry. It's not a great landscape to be getting your drinking water from, especially the closer you get to these urban centers here. This is kind of the urban line of Michigan right here. But so that's what they did. Instead of building this new proposed pipeline that would get their own water from Lake Huron, they instead decided to get their drinking water from the Flint River as it flows through the agricultural landscape of Michigan. So all sorts of lovely infographics were made about this, which I'll go through. This is sort of the nice for press version, and then I've got the details blown up on the next slide. But basically what happens is that in the water of the Flint River is contamination with these compounds called trihalomethanes. So tri meaning 3, halo meaning they are from the halogen family of the periodic table. And we call them methanes because they're all attached on to a single carbon, just like the compound methane. So the compound methane is just a carbon all occupied with hydrogens. This is methane. God damn it, there we go. That's methane. So we call this a trihalomethane because there are 3 halogens on a methane molecule where the hydrogens would be. And these trihalomethanes, these come from all of the many and varied industrial activities, everything from auto part manufacturing to paper milling to munitions making to, just industry generally. I used to live in Southeast Michigan, and my apartment was across the street from an old paper mill, so we had that contamination. The lake that we used to jog around was just downstream of a Ford manufacturing plant that built bombers in World War II. So there's, just like here, there's a lot of shit in the water. And so these trihalomethanes, when they get into water, they increase the corrosion, the corrodability of that water. Because these halogens have all sorts of free electrons hanging off of them, and they are very sticky to all sorts of things. And so in the city of Detroit, with its nice clean water from Lake Huron, they had a corrosion measurement of about 0.45. And in Flint, coming from the Flint River, was about 1.6. So that's almost 3 times. It's 2 point something-ish times more corrosive. So this is pretty high. So normally what you do to combat this, what you do to treat the corrosiveness of your water is normally you add phosphates. And this phosphate is very super sticky. It's very slimy. And it will coat to and stick to all of your water transporting infrastructure so that corrosive compounds can't interact with it. And the city managers of Flint said, oh, that's also really expensive. We don't want to do that. And so they didn't. So they didn't add the phosphate to the Flint water supply. So the pipes didn't get coated with phosphates to reduce the corrosion. And so they had lead pipes interacting with very corrosive substances, which basically put lead straight into the water. And so the whole city of Flint, for years, was living off of bottled water because they had to replace all their pipes because all their pipes were lead. We have a lot of lead pipes too, by the way. But by comparison to the Flint River, Lake Erie is clean. So they had to replace all their pipes. They had to pay for, they got sued at the app. They had to pay for damages for all of the small children who for years, for at least a year, were drinking this water. it's been a whole educational crisis, a whole developmental crisis, a whole medical crisis in the city of Flint in the years following this event. They're only sort of just now getting back to where they were before this, and Flint wasn't exactly doing well before this. This was a kick in the teeth that Flint did not need. So yeah, so that's what happened in Flint. A little bit more of a chemical explanation. I know I added all of this text before I uploaded the slides. I will re-upload this slides so that you have all this text. A lot of this text says everything that I already said. But just to kind of show you a little bit more chemically, not the infographically, what was happening. So here we have some beakers of water. And so here we have some water with high trihalomethanes. And in addition to phosphates, one of the things that you could do, like if this was just water not going through lead, one of the things that you could do is you could add this iron chloride. So here's what iron chloride looks like. And iron chloride reacts with these trihalomethanes and it forms this flock, F-L-O-C-K, like a flock of birds, but not like a flock of birds, more like you're flocking a Christmas tree. Folks heard of flocking a Christmas tree? Where you spray the snow on it, it gets all puffy. Yeah, so like you're spraying the snow on the Christmas tree and it gets all puffy. So the iron trichloride reacts with the trihalomethanes, forms this flock, it settles out, and then you filter out the flock and you've got nice clean water. So that's kind of the cheap way of dealing with those trihalomethanes, which is what the city of Flint did. They used this iron chloride to try and clean out the trihalomethanes. The problem is that, so if this is our trihalomethane, bromine, all sorts of halogens, what group is chlorine in? It's also a halogen. We just added more fuel to the fire with doing this. They tried to get out the cheap way, and they just led to more lead in the water. So this is what happens when you try to cut corners at the municipal level. This is why, yeah, this is what happens when you try to cut corners. Things go bad. The reaction that's supposed to happen when you add the phosphates, this is what's supposed to happen. So what's supposed to happen is you have all this stuff in the water, it pulls the lead into the water. Here's the lead in the water. You add the phosphates, and you end up with this lead phosphate complex that gets nice and heavy, settles out, gets trapped in filters, doesn't get into the water supply. That's what was supposed to happen. And that's what didn't happen. And so you would think that we'd be learning things from Flint, but unfortunately we're not. Unfortunately, we're not. So this is a link. This is an active link in your slides that you can click on if you want to go read the whole thing. That's a gift article from 12 Foot Ladder so that you don't have to deal with the Buffalo News paywall, because I'm not paying for it either. But so this is a new story. This is June of this year. So we're working on it. A lot of funds were allocated in the Bipartisan Infrastructure Act to help cities deal with replacing their lead pipe infrastructure. That legislation didn't get passed until something like 2022. And we have to then, agree on the actual disbursement of funds, come up with plans, hire contractors, blah, blah, blah. And so we're only sort of just now getting around to having a plan to spend the money allocated in the Bipartisan Infrastructure Act to replace the lead pipes that all of our cities all across the country have. So this is a story to keep an eye on. I'm sure I'll be talking about it in a little bit more detail the next time I teach this class, hopefully with a happier ending than that. All right, so that's my spiel about metals. Does anyone have any questions about metals? Anything you want me to go back to? Okay. All right. So now we're going to switch to a different group of chemicals, anions. So if a cation is something that is positive, what do you think is the thing that defines an anion? A negative charge. These are things that have negative charges. All right, so anions are not by themselves toxic. If you just held some phosphate in your hand, you're going to be fine. Sometimes we even just sort of directly add them to our food. We're fine. It's fine. Common anion compounds that we are primarily concerned with include phosphate. So we just had phosphate as the good guy. Now we're going to see phosphate as potentially a bad guy. Right? Everything has a dual nature. So phosphate is a common anion. It's actually -3. -3. I know the chemists will yell at me and say it's 3 negative rather than -3. So that's where I just drew it. So we're just going to live with it. So that's phosphate. And then this is nitrate. And the reason why we are concerned with anions from a toxicological standpoint is because excessive amounts of anions lead to a condition known as eutrophication. So eutrophication is basically too much nutrients. So not only are these negative compounds, but they are essential nutrient compounds. Organisms need these compounds to grow, especially plants, especially algae, my lovely algae. Love nitrate and phosphate, especially phosphate, way too much phosphate. So when you have too much of this phosphate and nitrate in habitats, especially in aquatic habitats, we're worried more about eutrophication in aquatic habitats than we are in terrestrial habitats. But in aquatic habitats, all of this extra nutrients fuels algal growth, fuels plant growth. And in the initial, that seems like a good thing, right? More plants means more oxygen, sucking up all that carbon dioxide. That's what we want to happen. But all things must die. And so eventually, there gets to be so much algae and so much plant growth that they block out the sun from themselves. And so they can't photosynthesize anymore because there's not enough sunlight. And so there's just all of this nutrients and they're trying to grow, but they can't grow because there's no sunlight because they're blocking it out. And so they die. And that means that we now have all of this plant growth decomposing. And decomposition is a heterotrophic process, meaning that we've ramped up bacteria Krebs cycles and we are sucking up oxygen. Sucking up oxygen means that there's not enough oxygen for the fish or the frogs or the crayfish or the zooplankton. Nobody else has enough oxygen because every bit of oxygen is going towards the decomposition of all of this plant matter. And that reduces the oxygen to such a point where everything in that water body will die, and then you've just got this decomposing mess. So eutrophication tends to result in some pretty bad things happening. We'll talk more about some other bad things that happen, especially with the algal blooms when you have too many anion nutrients like phosphate and nitrate. But in a nutshell, that's eutrophication. Now, nitrates specifically can result in a condition known as blue baby syndrome. We used to see blue baby syndrome due to nitrate toxicity a lot in the Midwest flyover agricultural states. So think like Kansas, Nebraska, Iowa, Missouri, think those sorts of places. Places where corn just goes for miles. I'm not sure if you all heard the recent news report about the corn sweat that was making it humid the week right before class started. Yeah, so that's another one to go look up. I don't have time to get into corn sweat now. But in all of those states where there is tons of agricultural activity, especially growing corn, wheat, and soy, all sorts of fertilizer is applied to those fields, mainly phosphate, nitrate, and some ammonia. And in a lot of those really rural places that don't have a lot of municipal infrastructure, lots of those homes are on well water, right? So there's just groundwater underneath them, and they drill a hole down into the ground, and you put a pump in there, and it pumps the water out of the ground, and you have running water in your house. Ta-da. Okay, so you've got all these fields, we're putting out all the nitrate on it, and all that nitrate, whatever wasn't getting used by the plants, was filtering down into the groundwater. And it was getting into the well water. And so the families were drinking this nitrate contaminated well water, which for grown-ass adults like you and I, doesn't matter. However, if you're a baby, it matters. because babies have a different form of hemoglobin than we do, especially if they're new. And, you know, and if you're bathing your baby in this, if you're not producing enough breast milk, you're probably giving them formula. What are you mixing that formula with? Your well water. So what is happening in blue baby syndrome? So here we have some hemoglobin. And if you recall, we've got some iron in the center of our 4 hemes that is going to bind to oxygen, oxidize it from its +2 state to its +3 state. And typically what happens with our hemoglobin is that the oxygen leaves and iron is reduced from its +3 to its +2. And all of this is done through the action of this methanohemoglobin reductase enzyme. So methanohemoglobin reductase is the enzyme that removes the oxygen and reduces iron back to its original state so that it is initially, again, attractive to some oxygen. Everybody with me so far? I'll give folks a moment to catch up. This is methemoglobin, sorry, this is methemoglobin reductase. This is a picture of the enzyme. So this is the enzyme that takes the oxygen off the heme and makes iron back into its +2 stage. All right, folks good? Okay, so that's how it's supposed to work. Now we introduce nitrate. So nitrate, NO3, in an aqueous environment does not exist as NO3 for very long. It very quickly gets broken down into this substance known as nitrite, NO2. NO2 is much stickier to hemoglobin, to that heme, than oxygen is. And especially if you've still got your baby infant hemoglobin, it's extra sticky, extra sticky. So because there's nitrate, if there's nitrate, we know there's nitrite because nitrate doesn't exist that long. It gets converted pretty quickly into nitrite. And it's the nitrite that ultimately causes the problem. And so because nitrite is so much stickier to hemoglobin, this enzyme can't remove it. The enzyme can't remove it. And so the nitrite remains stuck to the iron, keeps it oxidized, can't be reduced back to its original stage, and it can't pick up more oxygen. So in babies, they go blue because they are losing oxygen. They're going cyanotic because they cannot get any oxygen. They have to go to the hospital. They have to have their blood run through dialysis, right? It's like a whole thing. You got to have chelation treatment to get rid of it. It's a process. So it's not, I mean, if you catch it, it's not fatal. But, you know, imagine, 1920s before we knew this. This was a thing. And, I had a photograph on the last slide. It still happens every now and then. It happens far less. And lots of towns and counties have regular well water testing and treatment programs to catch, is your well having too much nitrate? Do we need to add something to remove that nitrate? Go get some bottled water. Don't drink your well water, right? They're like, we know about it now. And so we can kind of get ahead of it. But back in the day, it was a real problem. Okay, so phosphate nitrate, those are anions, eutrophication, blue baby syndrome. On the whole, if you had to choose your bad guy to be up against, I'd go up against an anion because these are surmountable problems. These are dealable, I feel. Other things, not so much. All right, any last minute questions about anions? Okay, so now we're going to move on to organic pollutants. So the rest of these chemical classes are all different forms of organic compounds. So we have to do a little bit of organic chemistry. So organic molecules are, of course, hydrocarbons. So we always start with a carbon, and if you remember, carbon has 4 free valence electron spots, so we can make up to 4 bonds, and it becomes the Lego block of life. We can fill up those spots with just about anything. Very commonly, we'll see carbons fully occupied by hydrogens. We would call this form saturated. So we call this carbon with maximal amount of bonding to only hydrogen. We call this saturated. Oh, how well I can write that word. Saturated. I'm just going to write sat. Saturated. So this is the saturated form of carbon. As soon as you start having other things occupying these bonds or other double or triple bonds, it is no longer saturated. So as soon as we start having things like hydroxide groups or nitrous groups, or even halogens, it is no longer saturated. But these are all things that carbon can bond to. And carbon can bond to so much more. These are not the only things that carbon can bond. All right. So as you are reading about these different chemical compounds that are organic, there are some common ways of phrasing or writing or naming things that you're going to see over and over and over. Yes, question. Yeah. Yes. Correct. That would be unsaturated. So in this, now with all of these different things, yes, that would be unsaturated. That would also be unsaturated with, yes. Yep. Maximally bonded to only hydrogens is saturated. Literally anything else is unsaturated. Yep. Good question. All right. So just some quick common themes in how we name and talk about organic compounds. So the first thing that you might notice about the naming of organic compounds is that those compounds can have either an ane in the name, an ene in the name, or an ine in the name. Whether you have an ane or an ene or an ine denotes how many bonds exist between a pair of carbons. So when you only have one bond between carbons, so one carbon single bonded to another carbon, that's an ane. So any compound that has ane somewhere in it, that implies that there's only single bonds. As soon as you, and I'm sure Montross would be like nails on a chalkboard to hear me describe this, but this is functional enough for our purposes. As soon as you have an ene, that suggests that somewhere there is a carbon-carbon double bond. It can be just one, it could be lots of them. Somewhere there's a double bond. And then finally, if you have an ine, that means somewhere you've got a carbon-carbon triple bond. And this means that I can now tell you the lamest organic chemistry joke. But I still remember this. This is the joke that my organic chemistry teacher way back in undergrad showed me. So let's see. So we've got, so we always start with a methane group, and then we go come on, draw. There we go. Oops, I messed up. This is going to be worth it, I promise. Just because it's not clear enough that that's a triple bond. It's a triple bond. So you know how sometimes chemicals have like a special name that, you know, someone back in 1830 just named it something and we've stuck with it ever since? This is one of those compounds. This is Old McDonald's compound. This is Old McDonald's compound because it's ene, O. Told you all it's going to be worth it. Okay. In any event, see, and now you'll forever and always remember enes and ines because of that lame compound. So anytime you see these phrases in your chemical name, that's to suggest something to you about how many bonds that there are. A lot of our organic compounds that we're going to be talking about are going to be called aromatics. And aromatics often means that they have a scent to them, but the other thing that aromatics really means chemically is that they have a ring structure. Typically, this is the ring that we begin to build an aromatic compound with. This ring, as it's drawn here, so when we have this ring, we have carbon-carbon single bond, carbon-carbon double bond, single bond, double bond, single bond. So there's 3 double bonds and 3 single bonds in this ring. And this is benzene. Right? We've got our ene. Double bonds. Benzene. So benzene is always our base for building an aromatic compound. And a lot of times we're going to be building our aromatic compounds names not off of benzene, but off of a very close relative of benzene. We're going to add an OH to one part. And this is going to be phenol. So here's our ene again. And all relates to that OH. So benzene is our base for aromatics. A lot of times here, we're going to be building off of phenol. So for example, here is the compound bisphenol A, also known as BPA. I'm sure you have seen products in the grocery store that say packaged with no BPA. This is the BPA that they are not packaging with. BPA was added to a lot of plastic liners to help make sure that all of the food product came out of the package. If you've ever had like an old ketchup bottle and ketchup was like stuck in there because that didn't have BPA, and then we put BPA in there and everyone's like, great, I can get all the ketchup out of my bottle. And then we're like, oh shit, BPA causes breast cancer. What do we do? So they take the BPA out, they put something else in, and now we can still get all the ketchup out of the bottle, but the stuff that they put back in has a lot of the same properties as BPA, and so we didn't really fix it. So it's a thing, but in any event, this is bisphenol A. And so to just sort of break down what we've got here, this is form A of bisphenol. So we can have it in a couple different permutations depending on stereochemistry beyond the scope of this class. But whenever we see bi, how many does that refer to? 2. What do we have 2 of? We've got 2 phenols, right? Here's 1, Here's two. Bisphenol A. That's all it is. We're going to be finding a lot of these hydrocarbon products, whether it's a straight chain or whether it's an aromatic. They are often created from fossil fuels and the byproducts of fossil fuels. We often think of fossil fuels purely as energy producing compounds, right? If we think about oil, natural gas, coal, things like that, we're often thinking about these in an energy producing context. But actually, this is especially true for oil. Most oil is actually for manufacturing processing. Most of our plastics are made from oil. Most of our industrial products are made from oil. Gasoline is almost a byproduct afterthought of that plastic manufacturing process. These organic compounds, and especially the aromatic compounds, were the particular focus of a book published in the 60s called Silent Spring. I used to have you all read that book as part of this class, but I have found that folks have a hard time relating to the language of Silent Spring these days. It's just a little too old, a little too flowery for a lot of modern tastes. And it was a whole book that you had to read in addition to the textbook, in addition to the primary literature that we would be reading. And so I've abandoned it in favor of focusing on the primary literature because I'd rather you understand that. But if you need a good summer read, highly recommend Silent Spring. It is the book that really changed the course of the past 100 years. We wouldn't be as tough as this class may be to hear about. It would be 100 times worse without the book Silent Spring in the world. So Silent Spring did a lot of good work for us. So Silent Spring really focused on organic compounds, especially organochlorine compounds. So these are organic compounds that have chlorines on them. Organochlorines act in many different ways on an organism's body. They typically tend to be carcinogenic, meaning that these compounds are interfering with cell cycle regulation. So anytime you see carcinogenic, think cell cycle dysregulation, interfering with those checkpoints. They interfere with a lot of other pathways too, but primarily carcinogens. The author of Silent Spring, Rachel Carson, ultimately died of cancer. Whether or not that, we unfortunately don't know if that cancer was attributed to these compounds or not, because she did work in environmental work with the government, with U.S. Fish and Wildlife. She worked exposed to a lot of these chemicals. So we don't know if these chemicals were in fact the cause of her cancer, but the fact that these compounds do cause cancer and that she also died of cancer is not a connection that should be dismissed, I don't think. Most notable among the compounds that were discussed in Silent Spring are aldrin and dieldrin. These are cyclodienes, like so. So cyclo in that they are, they're surrounded by these chlorines. There's our enes, suggesting that there's no bond somewhere, in which there are. These were often used as insecticides, sprayed massively on crops, roadsides. A lot of these compounds were sprayed into tropical areas to combat mosquitoes and other disease vectors, things like that. Hexachlorocyclohexane. So that's a mouthful. So hexachloro, meaning that there are 6 chlorines. Cyclohexane, meaning that you have hex, again, means 6, ane, single bonds, circled up together. Hexachlorocyclohexane. When you get to organic chemistry, that will make a lot more sense. And so now you'll hopefully be a little bit primed for that. Let's see, how many slides do we have to go? 3. We've got a few minutes. Okay. Polychlorinated biphenyls. We looked at BPA a little bit already. These are other compounds that are related to BPA. Generally speaking, BPA, bisphenol A, is in this class of compounds, polychlorinated biphenyls. So we abbreviate polychlorinated biphenyls to PCBs. So PCB stands for this. PCBs are entirely anthropogenic. You could wait around 100 million years and these compounds will never just form on their own spontaneously. So they are entirely anthropogenic. We have them primarily for industrial uses. They're very stable once you make them. They're very viscous, meaning they're thick and sticky like molasses. And because they are primarily hydrocarbons, they have fairly high lipid solubility. So they manage to get into your fatty tissues and stay there for a very long time. Most famous of the PCBs is DDT. DDT stands for dichloro-diphenyl trichloroethane. So here's DDT. DDT can be broken down into either one of these derivative compounds, but no matter what form it takes, it sticks around in the environment. It's highly lipophilic, stays in fatty tissue, and can persistently leach into the organism long after exposure. So when we think about what is in a PCB, so we have biphenyl. So here's our, sorry, I want to make that slightly bigger. I'm just going to make this a titch bigger so that we can see what's going on. All right, so we have our biphenyls. And I know we said phenol has an OH group on it, but because these are polychlorinated biphenyls, we've replaced the OH in phenol with more chlorines because more chlorines equals better in these compounds. So every available spot has a chlorine onto it. Anything that is not occupied by a carbon or hydrogen, we've slapped a chlorine on it, including where that hydroxyl group for a phenol would be. So 1 phenol, 2 phenol, all the chlorines. And that's true whether we're looking at DDT, DDE, or DDD. Okay, sorry, trying to kind of blitz through here. Other polychlorinated compounds. I don't really have anything particular to say about these other than that they exist. And in the interest of time, I just want to kind of fast forward to this very last slide of introducing organophosphorus insecticides. So organophosphorus insecticides like diazinon here. So these are organic compounds that have a phosphorus somewhere in them. That's what makes them organophosphorus compounds. And we primarily use these compounds as insecticides, meaning we're trying to kill insects with them. The way in which they work is they inhibit acetylcholinesterase. What the hell is acetylcholinesterase? So in your nerves, when your nerves are signaling to one another, one of the most common neurotransmitters, which is a neurotransmitter, is a compound that goes from one nerve to the next nerve to deliver the signal. One of the most common neurotransmitter compounds out there is acetylcholine, often just abbreviated as ACH. So acetylcholine, that is a very common neurotransmitter. So this nerve is sending a signal, and so it is sending out acetylcholine, and this nerve is receiving the acetylcholine, and so it is therefore now receiving the signal. That signal by the receiving nerve stays on. That signal is like on, until acetylcholinesterase, written here by the little yellow star, comes and removes the acetylcholine, right? Ester ACE, it's an enzyme that breaks down acetylcholine. So acetylcholinesterase turns off the signal. So imagine you stub your toe. You now have that nerve signal saying, oh shit, there's pain. Imagine that signal just on. You can't turn it off. You are perpetually stuck in I've stubbed my toe mode until acetylcholinesterase comes and turns the I've stubbed my toe signal off. That's what we're doing. But it's not just for pain, it's for literally everything. So your nerve signals are on, sending the signal is transmitting until you turn it off with acetylcholinesterase. Organophosphorus inhibits acetylcholinesterase. And so insects who are exposed to acetylcholinesterase cannot turn off their nerve signals. Their nerve signals just keep going and going and going. They're just pumping out acetylcholine, going, and they're basically nerve transmitting themselves to death. And that's how organophosphoruses work. And on that cheerful note, we're going to end. And I will stop the recording and I will post it pretty soon. And yeah, I'll let you all know when I posted the recording.